Have you ever stared at a really complicated circuit diagram and just thought, where do I even begin? Well, today we are going to crack the code. We're talking about Kirchhoff's laws, the two incredibly simple rules that are the absolute backbone of all modern electronics. By the end of this, you'll see exactly how they work. Let's get into it.
So you probably know Ohm's law, right? V equals I times R. It's a lifesaver for basic circuits. But then you run into something like this. You've got multiple batteries, wires branching off everywhere. Suddenly, Ohm's law by itself just isn't enough. It won't cut it. This is the exact kind of puzzle we're going to solve today.
The solution, believe it or not, is actually super elegant. It comes from a physicist named Gustav Kirchhoff, who, way back in 1845, laid out two rules. And with just these two rules, you can solve literally any circuit, no matter how messy it looks. These aren't just clever tricks. They're the fundamental principles that make every single electronic device you own work.
Okay, let's kick things off with his first law. This one is all about tracking the flow of electricity. You can think of it as the rule for electrical traffic.
So, Kirchhoff's current law, or KCL as we'll call it, is beautifully simple. It just looks at any point in a circuit where wires come together. We call that a junction or a node. And all the law says is this. Whatever amount of current flows into that point has to be the exact same amount of current that flows out.
The easiest way to picture this is with water pipes. Imagine you've got a junction where a few pipes meet. All the water flowing in from, say, two pipes has to go somewhere, right? It has to flow out through the other pipes. The water can't just vanish, and it can't be created out of thin air. Well, electricity works the exact same way. No leaks, and definitely no magic.
And here's the really cool part. The deep reason why this works. KCL isn't just some random rule. It comes directly from one of the most basic laws of physics, the conservation of charge. You see, the charge, the little electrons that make up the current, can't be created or destroyed. So for every electron that flows into a node, one has to flow right back out. It's that simple.
So, how do you actually use this? Well, it's a really straightforward process. First, you spot a junction. Second, you add up all the currents going in. Third, you add up all the currents going out. And finally, you just set those two numbers equal to each other. That little equation right there, it becomes one of your most powerful tools for figuring out what a circuit is doing.
All right, one law down. Let's move on to the second one. If the first law was about the flow of current, this next one is all about the energy in the circuit, which, we measure as voltage.
This is Kirchhoff's voltage law, or KVL. And what it says is, if you trace any path in a circuit that ends up back where it started, a closed loop, and you add up all the voltage boosts from batteries and all the voltage drops from components, the grand total will always be zero.
Now, my absolute favorite way to think about this is to imagine you're hiking. Think of voltage as your elevation. A battery is like a ski lift. It takes you up the mountain. It gives you a big boost in potential energy. A resistor, on the other hand, is like skiing down the mountain. You're using up that energy. So if you start at the bottom, take the lift up, and then ski all the way back down to where you started, what's your total change in elevation? It's zero. A circuit loop is exactly the same idea.
And you guessed it, just like the first law, this isn't some arbitrary rule. KVL is really just a statement about the conservation of energy. You simply can't get more energy out of a loop than you put into it. All the energy that the batteries supply has to be completely used up by everything else in the loop. It all has to balance out perfectly to zero. Now, the one little thing you got to keep in mind with KVL is that direction is everything. As you hike around that circuit loop, you have to track your ups and downs. When you move across a battery from negative to positive, that's a voltage gain. You're going up the ski lift. When you move through a resistor, that's a voltage drop. You're skiing downhill. As long as you get the signs right, it'll all add up to zero every time.
So there we have it, our two laws. One tells us about current at a single point, and the other tells us about voltage around a loop. When you put them together, they create a complete toolkit that lets you analyze pretty much any circuit you can imagine.
Let's just put it all together. On one hand, you've got Kirchhoff's current law. It deals with current at a node. It's based on the conservation of charge, and the rule is simple. What goes in must come out. On the other hand, you've got Kirchhoff's voltage law. That's all about voltage in a loop. It's based on the conservation of energy, and its rule is that any round trip has to add up to zero. So why does all this matter so much? Why should you care? Because these laws are not just for a textbook. They are the absolute foundation of all modern electrical engineering.
The circuits inside your phone, your computer, your car, literally everything with a circuit board was designed and can be fixed using these two fundamental ideas. They're the essential tools of the
When you really think about it, it's kind of amazing. Two simple concepts, you can't create or destroy charge, and you can't create or destroy energy, give us the power to understand and build our entire electronic world. It really makes you wonder, doesn't it? What other incredibly powerful rules like these are hiding out there, just in plain sight?
Thanks for watching.